All right, welcome everybody to Consolidating Infrastructure with Azure Kubernetes Service. How many people are holdovers from the last talk on containers? All right, I didn't lose that many people. Excellent. Anybody here using Kubernetes in production? Maybe 10 people? Okay, how many people here are familiar with Kubernetes basic concepts, like what pods are, replica sets, daemon sets, stuff like that? Okay, so we'll start off, we'll go through a little bit about those basic object types and things like that before we kind of kick off into AKS. So if you weren't here in the last session, my name's Eric St. Martin. I am a developer advocate for Microsoft, where I mostly work on open source, Linux, container-related things, and Go. And maybe there's more Go people in the room this time. I'm not going to ask because it's just going to make me feel bad. So first thing we're going to do is we're going to take a look at just the other offerings that we have for running containers inside of Azure. For anybody who was here the last session, it's just a couple of minutes. We're just going to breeze over them really quick. We'll take a look at how to deploy a Kubernetes cluster inside of AKS, how to deploy services to Kubernetes using Helm. And if we have some time at the end, we'll talk a little bit about how we might be able to make high availability clusters. Again, all the code's available at this link. I will put a slide up at the end for you to take a picture of as well. So Tailwind Traders acquires Northwind again for, I don't know, about the 10,000th time today. And we've decided that we want to use containers. We figured this is going to solve a lot of problems for us. And if you were in the last session, we talked a little bit about how containers are fully packaged applications with all of their dependencies bundled. They're easy to deploy with just a single API call from your container runtime. They provide us better resource utilization without overhead. So what containers aren't, they're not virtual machines, but I'm guessing most of you are Windows folks, so you can call me a liar because they are virtual machines in Windows. And they aren't a hard security boundary. There's a lot of controls we can put into place to make them a lot more secure, but we have to remember that these are not virtualized environments, that system calls inside of a Linux container at least are being made to the host's kernel. So moving from VMs to containers, we can get a lot more efficiency out of our infrastructure, save a lot of cash. If you don't like saving cash, please give us money. We're happy for that to happen. And we can get a lot of deployment and resiliency benefits, especially when we start talking about container orchestration. And if we're using tools like ACR, or if in the open source world, Harbor, Claire, things like that, we can start looking for vulnerabilities inside of our containers as well. So there's a lot of container offerings. Let's just talk really fast, maybe 2 minutes, about what other options you have for containers if maybe you're not at Kubernetes scale yet. So we have ACI, which is containers on demand. We have virtual machines we spin up for you. We run the container inside of that. You pay per second while the container is running. And you don't have to worry about clusters or provisioning virtual machines and setting up a container runtime like Docker and things like that on it. You get hypervisor level isolation. They can be hit using a public IP address, and it supports both Linux and Windows containers. These are great for very short-lived processes, mainly just because of the pricing model of them. But it's amazing for batch work, maybe doing machine learning model building, things like that. So if you're a command line person, it's pretty straightforward. You can do this through the portal. We walked through it in the last talk. I'm not going to do it here just for time reasons. I'd prefer to talk more about Kubernetes in this session. In the last talk, we talked about app services for Linux and web apps for containers, which is a fully managed platform as a service to run C#, Python, .NET, what am I missing? PHP, Python. Applications, but it also runs containers, web-based containers anyway. So we get a lot of features like metrics and things like that for latency and HTTP requests. Deploying is pretty straightforward. We're just doing an easy web app create. Now on to Azure Kubernetes Service. But we can't really talk about what Azure Kubernetes Service is without talking about what Kubernetes is in the first place. So Kubernetes is an open source platform framework, I guess you could call it, for distributed systems and doing automated deployment. It's also mentioned as a container orchestrator, and we'll talk a little bit about what a container orchestrator is. It was designed by Google based off of a system that they have called Borg. And that's used to deploy thousands or millions, billions of containers per week, and it's been that way for decades. And a lot of the team that built Kubernetes came from Borg. This stat is actually a little old, but there's thousands and thousands of contributors, and even more if you consider the ecosystem surrounding Kubernetes, things like Harbor and service meshes and things like that. So it's a very, very active and vibrant community around Kubernetes. So we said Kubernetes is a container orchestrator, but what does that even mean? So orchestration provides us a number of things. So it gives us scheduling. So we use advanced algorithms to determine the best place to run your workload based on current CPU utilization, memory, things like that, and the requirements of the individual workload. We get things like affinity and anti-affinity. We get this in two places in the case of Kubernetes. So we can get node affinity or anti-affinity, and this allows me to attract or repel a workload from specific nodes. So an example of this might be one of the nodes in my cluster has a GPU, and this workload requires a GPU. So I want to attract this workload to that. Okay. Or maybe it has some sort of custom SSDs or things like that where you want to run there. We also get pod affinity and anti-affinity, and that's where I can set up labels on my pods, and I can set up affinity policies that allow me to attract containers to the same node. I want these, or I require or I prefer them to run on the same node together, or I can repel them so that they don't end up on the same node together. We get things like health monitoring and metrics for free. We get automated failover when our workloads die. They find a new place to live. We get things like scaling, where the number of instances of our application can scale up or down on demand, or automated if you put in things like the autoscaler. We get networking for kind of east to west traffic between our pods, no matter where they're running within the cluster. And we get things like service discovery, because in highly dynamic environments where we're running lots and lots of containers and applications, and we're scaling horizontally, there's 10 instances now, 5 later, and they're bouncing all around, we need abilities to have our applications find each other without kind of statically programming these things in. So how does Kubernetes work? Like, what is it actually doing for us? And this is important because we often adopt these tools that abstract things and make things much easier for us. But the thing we forget is sometimes these are leaky abstractions. And understanding how the system works and what it's doing on your behalf can make it easier to debug these things. So we start with some of the basic Kubernetes object types that exist from the point at which you install the cluster. This isn't a comprehensive list. I think this is almost all of the default ones. And because it looks like we have a bunch of people here that aren't as familiar with what some of these objects are, I want to walk through all of these. And we're going to do this in a very, very fun way. Who likes cartoons? All right, so if we're going to walk through these things, we have Fippy Goes to the Zoo, and this is really cool, and there's also the illustrated guide to Kubernetes. These are both available through PDF online if you like this sort of fun stuff. So Fippy is the giraffe. And if I had time, I would narrate this for you all and come up with fun voices, but I didn't. So the first base thing that we talk about on Kubernetes is a pod. Now, a pod is the lowest level primitive that we can push to Kubernetes. And a pod is nothing more than a collection of containers. So if you were in the last talk, we talked a little bit about how containers are based on namespaces and what they can see. Pods are just applications that are sharing namespaces, like a network namespace, so that they can see the same network interfaces, see the same files, things like that, so that they can share data between each other. So it almost appears to them that the applications are running on the same host together, and they move together. With me so far? Head nods. It's late in the day, I know. OK. Next, we have replica sets. So a replica set is one layer above a pod, and this is telling the container orchestrator that I need a minimum number of these things running. So the cluster will take that. It'll constantly monitor to see how many of these pods are running anywhere in the cluster that match these labels. And it will either create new pods or delete pods to keep that number. We also have secret management and configuration management, where we can tell the API server can store these for us. And then we're able to mount them into our containers as either environment variables or files. So the important thing here is when we put it into Kubernetes and we just add that little bit of YAML to our pod spec, the application inside the container does not know how that file got there or how the environment variables got there. So if we start thinking about 12-factor applications, this is exactly that. And when we start thinking about like QA and production environments, your application can be designed in a way where it looks at a file for its secrets or its configuration if you use a config map, or environment variables, and then use those as, say, credentials for things. And the application doesn't need to know how it got there, what environment it's in, and in those particular Kubernetes clusters, you could set those secrets to be different keys or different URLs to other services. OK, so if you think about replica sets, deployments are like a level above that. So a deployment allows us to add kind of additional things like rolling updates and rollbacks and things like that. And how this actually takes place, I wish there was a diagram here, but how that's actually implemented is the deployment will first create the replica set. Let's say there's 5 nodes, and then you want to update to version 1. Now you have an update policy that says how many of those things are allowed to be down at a time as part of this rolling update process, as well as the minimum number of them that have to be running at any time. So we'll start with 5, and we'll say it's 1 that's allowed. And it's going to create a second replica set with version 2, and it's going to set the replica set to 1. When that pod is up and healthy, it's going to shut down one over here. And it's going to continue to do that until all of them have been migrated, and it's going to stop if that stops happening. And a rollback is just the same thing in reverse. So this gives us a really nice deployment mechanism to be able to do this. And when we think about containers having all of the dependencies needed to run the application, rollbacks become significantly easy. The registry has a bundled image of that old version and all of its dependencies. It's easy to just roll it back. And in fact, it's still cached on the host, so a rollback can take place pretty quickly. Then we have daemon sets. So a daemon set is a little bit like a replica set with a little twist. So we don't tell it how many instances of a pod that we want running. A daemon set means that I need one of these pods running on every node. And these are great for things like metrics, agents, or log shipping, maybe host-based intrusion detection systems that you may have. This is how you would ensure that whenever a new node joins the cluster, that this application ends up running on it. Then we have ingresses. So an ingress is when we think about our pods, all of the IPs that they have to communicate with each other are all private to the cluster. This isn't publicly accessible. How do we expose our services to the internet or to the outside the cluster anyway? So services, I don't think there's a page for that, but a service is actually how we define that. And we say any pod that has these labels is an endpoint for this particular service. And it basically gives us a load balancer inside the cluster. So this is how we do service discovery. How does service A find service B? it just communicates with the fake IP address or the DNS entry for that service that got added. Is everybody with me? Okay, heads nodding. Some people sleeping, I see it. So now ingresses allow us to kind of add a layer above a service, and this is how do we expose this service to the outside world. And there's a couple of ways this is implemented. One of them that gets installed into your AKS cluster at least, the default ingress, if you set one up, will use an AKS app.io subdomain for your cluster. So it'll be service name dot cluster name dot AKS app.io, and that DNS entry will get forwarded into your cluster through that ingress. You can also create a service of type load balancer, and that will provision an Azure load balancer with its own IP address for that service, and then anything that's directed at that IP address can route into your service. And you can also run these things inside your cluster with Nginx and things like that. There's a number of ways that ingresses are implemented. There's also cron jobs. So we talked about using functions as a cron job in the last talk. But if you're inside of a Kubernetes cluster, there is a way to be able to set up scheduled tasks, which are containers that are ran at some interval. Then we have CRDs, or custom resource definitions. This is a little bit outside the scope of kind of where we're at and kicking off and getting into Kubernetes, but they are really, really interesting because it's a really powerful way to extend Kubernetes. So the Kubernetes API is actually extendable. We can tell it about new object types. And we start using this stuff for things like self-service infrastructure. Examples of these things is something called the Open Service Broker, which is a custom resource definition that introduces new types into Kubernetes so that you have a YAML type that you create, for example, like MySQL, and you have a couple of YAML configuration properties. And when you post that to the API server in Kubernetes using kube control like anything else, Kubernetes goes out using a service principal and spins up a managed MySQL instance for you. And then there's things like bindings that we can do to have credentials created just for our application and connected to it using one of the Kubernetes secrets. And when we tear down the application, that credential gets removed. Or if we're bundling that stuff in, like, say, a Helm chart, which we will talk about, we're able to tear down the manage MySQL with the application when we delete it. So, okay, we made it through. So now let's talk a little bit about when we post those things to Kubernetes, what's actually happening behind the scenes. All right. Okay, so we have all of our object types. We can think about Kubernetes like a giant reconciliation loop. And it's actually a series of reconciliation loops. We're taking our declarative state inside of our YAML file. This is what I want to happen. And then Kubernetes is going to be constantly evolving the system toward that state. Now, the important thing here is in this distributed system that it's eventually consistent. Just because Kubernetes accepted your request, it accepted your YAML file, does not mean that all of this is done yet, nor will it ever complete. So if you ask for 1,000 replicas and there is not enough resources in your cluster, then it's going to fail, right? It's not able to fulfill that request, and you would see it in a bad state. Another fun fact, if you do set replicas to 1,000, watch what happens. It will actually take down your whole cluster, and I know that there's the magic of, but isn't Kubernetes supposed to prevent that? But if you don't tell the scheduler how much CPU and memory that your application needs, it's going to be happy to schedule all 1,000 of them. And if you don't have the resources, you basically saturate the CPU. The node can't communicate with the API server anymore. The API server is like, oh no, that node is down. I need to reschedule all of that work. And then it throws it across what's left. And this keeps happening until cascading failure, your entire cluster goes down. So please, please, please put CPU and memory requirements inside of your pod definitions. Anyway. Okay. So this is what a deployment looks like. We talked a little bit about it. How many people have seen YAML for Kubernetes definitions? OK, a few. So it's going to be a little hard. Can I point all the way over there? OK, so this is an important part. There's usually a kind in the API version that we have. We're going to give this deployment a name. And these labels are things that we can use to query the API for objects that have these labels. These are also important for things like services and replica sets. This is the spec. Every YAML file or type that you're creating is going to have a spec, and that's where the configuration properties are. So in here, we're saying we have 2 replicas, and this is the selector. So we're saying that any pod that has a label of app set to Nginx is considered a replica for this deployment. And this template is basically the same thing. Down here is the spec for it. We're saying which containers we have, in this case, an Nginx. We're naming it Nginx, and it's the Nginx image at 179. So this template is what gets replicated. So every time a new instance of this for the replica set gets created, that's the spec, the definition that's going to be used to create the pod. So we're going to submit that to Kubernetes, and Kubernetes is going to do its magic. And then we should hopefully get 2 instances. These are on 2 separate nodes here, but there are no guarantees that they won't end up on the same node. So be careful about that. And as I said, you can use things like affinity selectors to make sure that you don't have, say, you're running 2 instances of a really important service. You could use affinity selectors to repel them from each other so that they don't end up on the same node. So all of this is made possible by what's known as the control plane. So we have a couple of components that run on all of the worker nodes, and then we have a bunch that run over in the master components. I have etcd set here. You typically would not run those on those same nodes. You would have your own cluster of etcd. But there's only so much room on a slide, so there they are. So let's talk a little bit about what each of these components are and what they do, because I think it's really helpful to understand what's going on behind the covers. So etcd is a distributed key value store. It's extremely fault tolerant. You need to run an odd number of them because it uses a distributed consensus protocol for that. But you can think about this key value store as a path structure. So for example, we have replica sets, and that's a directory. And inside of that is some key, which is the replica set you're creating. But it has versioning, so every time these things change, we can look at them in time, and we can do long polls and watch. So I want to know when this particular key changes, or I want to know when the directory changes. This is important because when we start talking about how Kubernetes works, we'll notice that most of this is provided by etcd. So sitting in front of etcd is the API server. And this is the thing that transforms all of the requests from all of the other control plane components, including kube control when you run that, or kubectl, or kubectl, or people call it 1,000 things. Kubectl is a new one I've heard. So the API server transforms those requests, authenticates, all of that good stuff, and puts the data or retrieves the data from etcd for you. Then we have the controller manager. So in this example, we talked about a replica set here earlier. So this is a standard replica set. So how does Kubernetes implement this? So the controller manager is just hitting the API server, looking at replica sets. It's going to look at those labels. It's going to call back out to the API server and tell me, how many pods do I have matching this label? And then if that does not match, we're going to either create or remove pod specs from the API server. Its only job is to look at the API server at one thing and create new objects and add them to the API server. And we'll notice this is a common pattern. And this is important because these components can die and restart, and they don't lose any data. They just reconnect and start at a certain point in time and tell me all of the events that have happened since. So the scheduler, the magical scheduler. So inside of the scheduler, it uses an algorithm called bin packing to decide which node your work is to go on. That part, sure, is complex, but when we think about what the scheduler actually does, it never actually interacts with a node. So the scheduler is going to wait on the API server and say, tell me about all of the pods or cron jobs that don't have the node name property assigned. Then all it's going to do is run its algorithm. It's going to set that node name back on the pod, and then it's going to give it right back to the API server. Job is done. That's all the scheduler does. Fun fact, you can actually have multiple schedulers in your cluster, and you can tell a pod which scheduler to use. That's a little bit of advanced topics if you have unique use cases, but sometimes this is important because you need outside information to make scheduling decisions. Maybe you're doing things based on network or things like that. We're almost through, I promise. I see people sleeping. So Kubelet is the one that actually interacts with the nodes. It's what does the better majority of the work. So it's going to be polling, looking for pods that have its node name. And it's going to say, OK, that's me. And it's going to interact with the local container runtime, Docker in this case. And it's going to see whether this container is running. And it's going to start it if it isn't. If it's noticed one in the API server that's been deleted and it still has running, it's going to delete it. And it's basically just going to be reconciling these things. It's also the thing that pulls images from the registry, mounts volumes to the container, mounts secrets. It does a lot of stuff. All right, Kube Proxy. So when we talk about services, we usually have an IP address for our service, but that's not a routable IP. It's a completely made up IP. There's just a block that we configure Kubernetes to use this IP address. And the only thing that it's routable for is containers inside of the cluster. And how this is accomplished is the Kube proxy is constantly monitoring the API server, looking for services. And then it's going to look at the labels that are configured on the service. And it's going to go find all of the pods that are in a ready state that have that label. And then it's going to configure IP tables rules on all of the nodes so that anything that tries to route to this cluster IP, this made-up IP, is going to get load balanced across all of the available instances of that service. CNI is a little bit of a advanced topic. It just works when you install AKS. You don't have to think about it. But you can use a network plugin. And CNI is responsible for mounting network interfaces into your container, especially for pod-to-pod communication. There's a couple of components, so you can create your own CNI thing for creating the interfaces. And then there's an additional plugin we can see down here, if I can find, there we go, IPAM, and that's the IP allocation module. That's when the pod gets started up, what application do I execute to find my IP address or to return it when the container goes down. This stuff isn't crucial to remember, but knowing it's there is helpful. So on to Azure Kubernetes Service. As we just saw, the Kubernetes architecture is fairly complex. There's a lot of components that do things. When things fail, they can fail in very interesting ways. So if you don't like managing all of that type of stuff, AKS is a very good option for you. We manage the entire control plane for you. So there are the couple of components that run on the worker nodes, which is Kubelet and Kube Proxy. But everything else runs inside of Azure for you, and you don't pay for any of that. So there's not VMs spun up for those master components that you're paying for. It's just provided as part of your cluster for free. You're only paying for the number of worker nodes. So another fun feature that we have is you can check a box and get Azure Monitor. So all of your pod metrics and host metrics just go straight to Azure Monitor and Application Insights, and also export all of your logs to Log Analytics, so you don't have to worry about doing any log aggregation. And some of the fun things are single command scaling and upgrades. And I'll tell you a story. This is how comfortable I am with the upgrades, and I hated upgrading when I managed Kubernetes clusters manually. I did 3 upgrades on my Kubernetes cluster last night because I'm daring like that. It was 1.9, and I was like, I can't do a demo on 1.9, and you can't do major version upgrades. So I upgraded from 1.9 to 1.10 to 1.11 to 1.12, all in a row, and if the demo gods favor me, my cluster still works. So Creating an AKS cluster is actually pretty straightforward. If you're a command line person, you can do an AZ AKS create. You just need a couple of options, the node count. If you look at the enable add-ons, that's me enabling Azure Monitor. And the HTTP application routing is when we talked about ingresses, or if you created an ingress for your service, you could get an Azure-based AKS app.io subdomain for that service to expose it to the internet. That's what the HTTP application routing is. Generate SSH keys is so that if I want to be able to SSH into my worker nodes, then I get the credentials to be able to do that. And because from last talk, I remember there is a lot of Portal fans here, we will take a look at creating a Kubernetes cluster inside of the Portal. So it's pretty straightforward. We're going to pick our subscription and a resource group. We give our cluster a name, pick a region. We can select from a variety of Kubernetes versions. The DNS prefix, so inside of your cluster, whatever you want the services to be able to resolve to. Cluster.local or whatever. So all of your services, service a.cluster.local. Then we're going to pick our SKU that we want. And this is the VM sizes that we're going to have inside of our cluster. Currently, we just support one node size. It's important to remember this, that once you select this at the moment, when your cluster is set up, when you scale to have more, you're going to get more of that same type. Now, a feature that is in progress, I don't have the delivery date on that, so I'm not going to say it, especially not on video. But we are working on availability sets where you would be able to have multiple SKUs inside of your cluster, say GPU nodes and CPU nodes, and you could scale the number of them independently of each other. So that is coming. Virtual nodes. This is actually really, really cool. I got to work on this project, a lot of fun. We talked about ACI a little bit earlier with those short-lived things. So what virtual nodes does is it installs a component into your cluster that pretends to be another node in your cluster, and really it's just an app. And then any pod that gets scheduled to it gets spawned off into Azure container instances. And this sounds really crazy, and you're like, why would you do that? If you're familiar with something like Kubeflow for doing TensorFlow on Kubernetes, that's a prime example. When you try to do the model, you could spin out 100 workers for TensorFlow, and they would all run in ACI, and your Kubernetes cluster itself never has to be any bigger than your normal everyday workload. Okay, so under our authentication, we can create, you should really enable RBAC. Please enable RBAC. I'll find you. So if you need a service principal for your cluster infrastructure, this is especially important if you use something like the cluster autoscaler, which we'll talk about. Networking, if you want to be able to, this is our HTTP application routing, that flag I turned on before. But underneath the networking configuration, this is if you want to be able to put your cluster in the same VNet as maybe you have some virtual machines or other things inside your cluster, or you can create your own VNet. Monitoring tag, that's just being able to send things to Azure Monitor and export the logs to Log Analytics. So it takes about 10 or 12 minutes for a cluster to deploy, so I already have one running, just so that we can maximize our time here. Okay, so once Kubernetes is installed, we can do an AZ AKS install CLI. What this does is just install the kube control command locally if you haven't installed it another way. And AZ AKS get credentials is how you're going to get the kube config for your cluster. So this is how you authenticate with the API server. So once we have our cluster running, upgrades are actually really, really easy. So in this case, we can do an AZ AKS get upgrades. And what this is going to do is it's going to tell us the version that our control plane is. That's the master version. And it's going to tell us what version of Kubernetes our worker nodes are running. And then it's going to tell us what versions we have available to upgrade to. And if you'll notice here, this is, I copied this a while ago, so there should be more. But you'll notice here that only 1.9s are available. but we've got all the way up to 1.12, and that's because we can't do a major version update. So you're going to have to upgrade to 1.9 first, and then you can upgrade to 1.10. And this is a rolling update process. So we talked about how that rolling update of your pods work. Well, the rolling update of your cluster behaves the same way. About every 10 minutes, Azure will add a new VM to your pool, to your cluster, with the new version of Kubernetes running on it. And as soon as that's up and healthy, it's going to mark one of your old version nodes, in this case, your 1.8.10 node. It's going to mark it so that it's not eligible for scheduling, so the cluster won't put any new work on it. And then it's going to drain all of the work off of it so that it gets scheduled elsewhere in the cluster. Once all of the stuff has shut down and it's running somewhere else, it's going to shut down that node. Then it's going to add another node of the new version, and it's going to keep doing this at about 10-minute increments until your entire cluster is up to the new version. Okay. So inside the portal, I will pull up my cluster, one of them. We can't see the drop down here because I upgraded it all last night, but had I been running an older version, we'd see them, the available things that we could upgrade here, and we just select the version, click save, and we wait till it's all done. Okay. So next. So scaling is also quite simple. Single command we can do, we just need the name of our cluster, its resource group, and the node count. This can be more or less than your cluster is currently running. It's just going to figure out whether it needs to add nodes or remove them to meet that desired node count. And if we look at it in the portal, it's pretty straightforward as well. We're just going to scroll this up, and we're going to say, give me 5 more. And thankfully, I'm not paying for this. Otherwise, I would not do that live. We talked about the cluster autoscaler. So what is the cluster autoscaler? So if you install the cluster autoscaler into your cluster, it's going to look at the total capacity that you have and resource utilization within the cluster. And when it passes certain thresholds, so say you have 5 nodes in your cluster and you're running at 90% CPU, that's not good. There's no room for failover. What happens when a node dies? There's no room for all of that to fail over. So what it's going to do is it's going to use a service principal to go out and add another node to your cluster for you. And when the workload comes down, it can also scale back down so that you're only running the minimum number of nodes that you need to based on those thresholds. Okay. So anybody familiar with Helm? Okay, a couple of people, maybe 3. So Helm we can think of as like a package manager for Kubernetes. So we talked about these YAML files that we create, but the problem with deploying an application is usually we need multiples of that. We'll have our deployment, we might have a service. If it has secrets or config maps or all of these things, we might have 5, 10 YAML files that have to be deployed for our application to be live. And what happens when we have to roll back and multiples of those things were modified? So Helm is really a way for us to take all of those things, and we get 2 things out of it. We can deploy them all as one unit, and we can roll them all back as one unit, all of these individual YAML files. The second thing it gets us is the ability to templatize this and override things. So I can say deploy WordPress, right? And then whatever the defaults are, it's going to install. But I'm also able to override parameters inside that chart and maybe deploy one of them with a different version. So I can run them side by side, and they're different versions of the app. And we'll take a look at what a Helm chart looks like. So there is a repository of pre-created charts that exists. So I used WordPress as an example. You can actually type Helm install WordPress, and WordPress will be running in your cluster with its own MySQL and all of that, and you had to do nothing but type a single command. So we can really think about it like package manager. We also have some that are Azure specific. So Azure's WordPress will deploy managed WordPress or managed MySQL for you as part of the install. Okay. Okay, so the structure of a Helm chart is pretty straightforward. We have a chart.yaml. This is just metadata. What's the name of the chart? What's the version? All of that good stuff. Values is going to be the defaults that are going to be placed into it. And then templates, these are the individual YAML files that are actually the things that go to Kubernetes, except they have placeholders that are going to be replaced by the things in the values.yaml or the things you overwrote it with. And because I know none of you are Go people, this is going to look really awkward. But we're going to take a look at the a Helm chart, and the template format is the same as Go's programming language. So we just have the YAML file that looks just like the YAML file we would have created for our deployment, except we have a couple of these placeholders here. Full name, the chart.name, chart.version. And we've talked about how in this values.yaml, you'll see these things exist, right? So here's our replica count, image registry, repository, all of these things. So these are just getting stuffed into that when you do the Helm install. And then on the command line, we can do a -- set and override any of these. So if I wanted to change the port, I could just set image.port equal to something else, and then that instance of this whole bundled application would just have that one override. Or we could override the repository or something. Okay. So Helm's pretty easy to install. We just need to do a Helm init once it's the command line's installed. And that installs an application called Tiller into the cluster, which is the thing that makes all of this happen when you post the chart itself up. In Helm 3, Tiller won't be a thing, so you probably don't have to worry too much about it. But it's good to know that that's supposed to be in there. So let's look at deploying a Helm chart. And I already have this, so we don't have to wait for it, but I want you to see what the command looks like. And I've overridden a whole bunch of stuff just so you can kind of see. Okay, so this is our Helm command. So we're installing it. We're giving this application bundle a name. So when we see it in the cluster, and I'll run a command where we can list it, and we can see that's going to be its name. The Kubernetes namespace that we want this to be installed into. And here we can see that I'm overriding a bunch of those values. So I'm changing the image registry to my ACR. I'm enabling ingresses. I'm setting some hosts in here, changing production URLs, which are environment variables. So you're seeing me override a bunch of stuff that was in that values.yaml file. Okay, so if we let that run for each of our services, this is what we get. Wow, at this font, that's really hard to read. So here's our front-end application Helm chart, our inventory, and our product, and we can see that they are all deployed. Now, exposing services. So we talked a little bit about having an ingress into our cluster. So we can create an ingress, or we can create a load balancer, which creates an actual public IP that routes inside the cluster, but we don't get things like SSL termination or caching or things like that out of the box. We would have to install things into our cluster. We'd have to manage more services, things like that to be able to accomplish that. So one thing I've loved doing in recent deployments is putting front door in front of the Kubernetes cluster, in front of the ingress that gets created, I should say. And this allows us to do SSL termination and caching and things like that for the cluster. And we'll take a look at that. So was anybody at the talk earlier where they were talking about front door? A couple of people? Okay, so yeah, front door is actually really, really interesting. So there's currently 64 locations where the front door exists. And when you try to hit my URL for my front door, it's going to hit the closest pop to you. And that's where your connection is going to be terminated. It's where your SSL is going, SSL termination is also going to take place. But each of those things knows the latency to all of the backends that you have, like if you have multiple clusters and things like that running, or if one goes down, things like that. We also have firewall rules and DDoS protection built in. So it's an extremely useful thing to put out in front of your cluster and not have to worry about a bunch of tools that you run inside your cluster to do this. So let's take a look at front door really quick. And I already have, oops. I already have a front door sitting outside of my cluster. Where's my front door? There we go. Okay, so front door designer. So in here, we create a front-end host. So in this case, I'm just using a free one from Azure. But we could come in here and we could use a custom host name. Now, once we set up a custom host name, it's going to require, if I do test.com, it's going to require that I set up a CNAME in DNS to prove that I own this, and so the traffic forwards. Once that CNAME is set up, you can actually have Azure create the SSL certificate for you, so you don't have to manage the SSL certificate by yourself. It just works. So that's a really, really fun feature. So once we have a front-end host set up, this is the URL that people are going to hit. We have something called backend pools. Now, these are all the endpoints that this could route to. So in this case, this is my front-end service. And I have two backends because I have two Kubernetes, identical Kubernetes clusters running, one in Eastern US and one running in Western US. And I want to be resilient to maybe a whole region outage or a natural disaster or even just load, or I just want to send West Coast people to a West Coast data center. There's a variety of reasons why you want to do this. So I have two identical clusters running on both sides of the United States. And these are the ingresses that I exposed for each of those services. This is just setting a path to hit if you want a custom health probe. We're saying whether or not the front door should communicate with my backend through HTTP or HTTPS, the interval at which we should do health checks. So every 5 seconds it's going to be hitting. And remember, all 64 locations are going to be doing this because they all want to know whether they can route traffic to you and what the latency is. And we have some load balancing configuration. So I've set up things for each of the 3 services to route. And these are the paths. So here we can see this particular case, I have an API health backend. OK. Now we have routing rules. So a routing rule is allowing us to say things like, when I hit this particular front-end host, I want to send it to this back-end pool if the connection is HTTP or HTTPS. Remember, SSL will terminate at the front door, which would still allow it to communicate over HTTP back to you. That's not what this is saying. It's saying to the client, the end user, what's the connection type. And if the patterns match this, the paths that they're hitting. We have some advanced features like URL writing. If we want the forwarding protocol, this is what we want to communicate with the back end. So for example, if I say match request, that means if you hit the front door using HTTP, then the front door is going to communicate with your back end service using HTTP. If you hit it at HTTPS, it's going to do that. It's going to match the protocol. And we can do some URL rewriting, and we can enable caching at the front door if you have some static assets and things like that that you want to cache. So pretty straightforward. So here is, as promised, we just looked at that. So I'm going to delete. I don't even know which cluster I'm in. Doesn't even matter. We're going to purge because I really want to delete it. We're going to delete the front-end service now. So I believe this is the East Coast server that I'm hitting. Let's see. Kube control config show context. No. What's the? That's not important. OK. So we just had a catastrophic failure. Our service went down. And this front door is still working, even though that the one backend is completely down. It's just routing everything to the other cluster. So catastrophic failure, we just kind of demonstrated that a little bit, that if one of the clusters went down, the region, natural disaster, a variety of reasons why a particular ingress or endpoint on one Kubernetes cluster may be down, we can safely route traffic elsewhere, or we can balance our workloads in multiple regions using things like front door. So I talked about that. I have duplicate clusters in different regions. We can either deploy to each of them using some specific strategy where these clusters have specific use cases and we're using the front door to route you to those. We could duplicate everything, and you can use things like Heptio's Arc, I think it has a new name now, for automatically replicating things. So if I install something into one cluster, Arc would automatically install it into the second cluster, so you don't have to do any of that manually. What about data? Data gets a little more complicated. So if you're using something like Cosmos DB, you have options automatically to replicate just doing read replicas or multi-masters for writes in different regions, and you're going to get that for free. The SQL database offerings have different replication strategies. I'm actually not sure about SQL Server, but Postgres and MySQL are going to replicate the backups for you into different regions, but you would need to restore a new cluster there. But hopefully in the future, we will start seeing things like Cosmos where you can do that. So we already demoed AKS with front door. So if you want to learn more about this stuff, all the documentation is available at these links. And I'll give everybody a second to take pictures of this. I'm also always available to answer questions. I love being hit with random use cases. Okay. If you haven't taken this picture in other sessions, it's the same slide. This is where you can grab all of the decks for all of the talks you've seen at the tour. And all of the code is also available on GitHub for all of these demos. And if you want to answer questions, I can do it for a few minutes, but they kick us out pretty fast here. With that, thank you so much for hanging out to the end with me. I hope you had a great conference. Thanks.